Welcome everybody to Introduction to Deep Learning. Today we're gonna continue talking about how we train neural networks. So very brief recap from the previous lectures. So specifically we've talked a lot about optimization in the last two lectures. In more detail we talked about gradient descent. We talked about how we do gradient computations with backprop. So we're getting our partial derivatives for each of our unknowns in our network, right? For the biases and for the weights. Again, note all three indices that indicates which layer, which neuron, and which weight in a neuron we're currently dealing with. We have these architectures with input layers, hidden layers, and output layers. We have loss functions, and we have nonlinearities such as reloss. Then we talked about making the gradient descent method practical, meaning we talked about stochastic gradient descent. So instead of computing a gradient over all training samples simultaneously, we are now taking the gradient just over a subset of samples, which we call mini batches. These mini batches go from 1 to m here. And then basically we're computing the gradient with m samples, which is m training samples in the current mini batch. And then the k here becomes the kth iteration, which means using the kth mini batch. So this made it practical by basically saying, well, we're taking a subset of the samples in our training set, and the subset gives us a good enough approximation of our gradient that we can then use to do our gradient update and then iterate and continue training our neural network. And in the last lecture, we also talked about gradient descent with momentum. Basically, we talked about can we exploit the fact that we kind of keep track of the history of gradients that we have done during the steps. So momentum was this kind of idea. You kind of accumulate gradients in a certain direction when it's always the same thing. So you have this exponentially weighted average of the gradient. So velocity is basically this accumulation. It's a vector valued variable that we store, and it comes at a pretty minimal cost. So the only thing we have to do is make this addition here, this vector valued addition. And then we're using the velocity to do the respective update steps. And we've talked about a lot of different variations of this one. We talked about momentum. We talked about RMS prop, which is the opposite in a sense of saying like, okay, let's penalize gradient directions where we have a high variance. So here, right, in this case, we have the y direction where we have more fluctuation, and in the x direction we have a more consistent gradient that goes always in a similar direction. And the idea of RMS prop is to make sure we're dividing here by the variance. That's also called the second momentum. So we kind of have this this idea of the variance of the gradients that we kind of computing by using the square root of the gradients, and then we're using this dampening function that scales the respective values. Okay, then we can increase the learning rate, it gets better. And then finally, we talked about ATOM, which combines momentum RMS prop, which is de facto the standard optimizer that most neural networks use today. Okay, so now we know a lot of things actually. So most of the basics we know now. And in this lecture, we're gonna talk a little less about the theory, but rather we're gonna talk about a couple of practical things to make sure we can actually utilize these tools that we have now learned in the previous lectures. And this comes to training neural networks, right? So we have to talk specifically about the learning rate. And the learning rate, I already mentioned it many, many times, is probably the most important hyperparameter in the entirety of the whole neural network stuff. And what happens here is that the learning rate controls how far or how much we trust a certain gradient computation that we have done, right? So if we have kind of a linear function, right, our gradient is going to be always constant. And if we have a gradient, we can just go infinitely far and we know, oh, we can trust this gradient. But now we have a very highly nonlinear function, actually, in our case, in the case of neural networks. So in this case, well, it depends really on the function, on the data, like how much can we trust the respective gradients. And this is what happens here in practice. So we have here, an interesting figure which basically says, well, if you're having a certain learning rate, and this is our training curve, and we're hoping that our learning our learning basically minimizes our loss function, we hope to find the ideal learning rate such that this works. So what could happen is if we having a low learning rate like the blue curve, the problem is basically, well, it works, everything works out, it's just going to take a long time. So like, going down with our optimization is unfortunately going to take a long time, especially at the beginning, like in this regime at the beginning, this might take too long. And when we're talking about network training, right, like it's not just a few hours, it might be even days or weeks that we're losing here in terms of training time. So this is happening when we have a too low learning rate. If we're having a high learning rate, like this green curve here, what this means is it goes down very quickly at the beginning, but then it doesn't go down that much anymore. And the reason why that happens is, and we'll get to this in a second, is basically, well, we're kind of bouncing around the optimal solution. Or like we're bouncing around the current local minima. And what we need to do here is we just need to lower the learning rate. In a more extreme case of this would be even if we have a too high learning rate, then we don't even converge anymore. Like if it's very high, the learning rate, it might actually turn out that we are diverging. Because what happens then is like we're getting, with one gradient step, we're getting further away from a local minima. Then the gradient becomes even larger because we're further away, and then like this kind of accumulates. As you go further away, your gradients become bigger, but because your learning rate is so large, you're actually overshooting even more than you would have done already. So the ideal scenario is we want to find like something like the red curve, which is essentially like on hyperparameter optimization, right? It takes a lot of effort to find that one, where it goes down quickly enough at the beginning, but doesn't stall and converges actually to a good solution. And you can even see that, for instance, in this case, the red curve doesn't go down as much as the green curve. However, at some point, the red curve goes clearly below the green curve, and they are roughly approximately similar. So for the most part, we don't have to fully find the optimal learning rate at the very beginning. So if you're a little bit slower here, this might be fine. But we want to make sure we are reasonably fast. And because of that, we want to make sure then that at the end of the learning, we're going to find a very, very low loss function. Okay, so this problem with the learning rate is basically this whole overshooting issue, right? So I mentioned this now a couple of times. So considering we have a two-dimensional function space here, and what we do is we're computing a gradient, right? The gradient points roughly this direction, gradient points roughly in this direction. And if we're keeping this learning rate roughly the same, right, you will see that, we kind of overshooting here from here to here. And that's a problem. So when we are far away, it's okay actually to have this high learning rate. But when we are close to the optimum, then we're going to overshoot too much. And that's what's happening here, right? So we're going to just overshoot too much. And we're never going to converge to something that is reasonable. So basically, the closer we get to our solution, the lower we would like to have our learning rate. So in other words, what this slide should tell you is that it's very difficult or, well, pretty much impossible to have a learning rate that stays the same during training and yet produces good results. Right? So in other words, what we have to do is we have to figure out a way how we adapt the learning rate during training, right? So what we would love to have is we love to have a high learning rate when we are far away, and we like to have a low learning rate when we are closer. And far away and closer in a training setting practically means, well, at the beginning we want to have a high learning rate, and later during the training, presumably we've done something reasonable during the training, we actually want to lower the learning rate to a reasonable level, right? And there's a lot of things what you can do basically to adapt that. And a very common methodology what people are implementing in practice, and this is very important actually, is a thing called learning rate decay. So learning rate decay means, well, we're starting with a relatively high learning rate, and as we're going through our iteration, through our epochs, we actually step by step lower the learning rate at a certain level. And one way to do this is kind of this having this exponential weighting of the learning rate over time. And this is one way to do it. So we're starting up with an alpha 0, which is our learning rate at the beginning. And then we're having a decay rate, which is 1.0, for instance, and we just have this incremental update step, which is just 1 over 1 plus decay rate times epoch times alpha 0. And since this is done every epoch, right? Every epoch we're going to change the learning rate right now, we're going to get a function that looks like this, right? It's this exponential decay that starts at 0.1 here and then goes down as we go and iterate. But we're never going to go to 0, but we kind of have this exponential function that approaches 0 at a certain level, right? So this is a very common way to deal with the learning rate. And now we have two hyperparameters. So now we have a hyperparameter alpha 0, which tells us how we should start. And we have a decay rate, which is another hyperparameter that tells us how far or how fast the learning rate should decay over epochs. And this is very common that the learning rate is being changed during the epochs. However, this is just one very naive example. This is a very common example, like doing a learning rate like this one. Doing a learning rate decay like this one. But there's actually many options. So one option is the step decay. Step decay means we just say alpha is alpha minus t times alpha. We do this every n step, so every epoch or whatever. T then becomes the decay rate, which is often 0.5. Right? So every time we're subtracting half of the learning rate. We have an exponential decay, which is t to the power of the epochs times alpha 0. Again, alpha 0 is the initial learning rate. Epoch is, the epoch, and t is our decay rate. T should be smaller than 1.0, which means it's actually decaying over time. And there's a lot of different options like these ones, and you can imagine people were quite creative when they came up with different learning rates, schedulings. And it turns out this is actually quite important because, as I said, at the beginning we want to have a very high learning rate. And as we go and move forward in our training, we want to have a lower learning rate. Okay, so now we have a learning rate decay. This brings us to the more extreme version, which is kind of like a manual version of this. This is something people call a training schedule. So training schedule, like a learning rate, is a training schedule. It's just one that is procedurally generated. One way to do it also is to just manually specify a learning rate for the entire training process. So for every n epochs, you just say, well, this is the learning rate that we want to have. How do we figure it out? Well, it's a trial and error way, right? So we just go ahead and we train. We check how our training loss looks like. If our training loss doesn't go down anymore, then we might want to reduce the learning rate. And we might do this by just looking at the curves. If you've done this a couple of times, you're going to get a bit of experience. And then, it eventually generalizes to some degree. The couple of things we have to consider here is basically epochs, training set size, network size, and so on. Now, one thing that should be very obvious here, like this is very hand wavy, right? Like, okay, we had a couple of things right now here, like different learning rate decays, how we can do that. But you should see this is very hand wavy. What I'm explaining to you here is there's no like perfect mathematical definition of how to do your training schedule. And this is probably the one reason why training neural networks is so empirical. In other words, we have to try out a lot of stuff and we have to see what works best. And trying out a lot of stuff in practice means you're going to train, you have a learning rate, you check out how your curves look like, and based on that, you're going to adjust your training. And a lot of times, and we'll get to this in this lecture actually, is training a network means you have to manually monitor how your loss functions, how your training curves look like. The training curves is, by the way, the number one thing we have for debugging here, because that tells us how our optimization is currently doing and how well and how much we can minimize our function. So this makes it very empirical and makes it actually quite time consuming from a manual perspective, which is a little bit ironic because, we started this whole endeavor of machine learning with the premise of, let's kind of try to get rid of like handcrafted design choices and let's automate things and learn from data. But now we're learning from data, but during the training, it actually is not so straightforward. So we have to monitor the training processes actually quite carefully. All right, so now we have a learning rate schedule. If we're going back to our basic recipe for training, the way the whole thing works now is we have a data set with labels, right? So we have pairs. X is, for instance, an image. Y is, for instance, the label for the image. And we have these ground truth pairs. And for the time being, everything, again, we're doing is here supervised. So we're always going to have these ground truth label pairs that are given by our respective training set. Xi is, for instance, the ith training image with the label yi. And in practice, you could see that the dimensionality of X is typically pretty much larger than Y, right? Like for classification, for instance, X has a dimensionality of how many pixels you have in an input image. I don't know, like 224 squared or something like this, depending on what architecture you're using. And Y is typically relatively low because it's, it's the class label eventually, or the respective scores that we care about at the end of the day. I is how many I's do we have is the question of our dataset size. It really depends on the problem, right? There's smaller datasets like MNIST or so is a pretty small dataset which has like tens of thousands of images. But in practice, if you want to deal with real images, you want to have at least 100,000, probably millions of images. Again, depends on your network, depends on your problem statement. But in practice, it's very obvious that X for classification problem is much larger than Y, dimensionality-wise. And you need, millions of images probably in practice to train a real network. Then you take the network F, right? You have its parameters, the weights and the biases. And we're using our favorite SGD variation, which in practice is Atom, to find the optimal parameters for the weights and the biases. We get the gradients from backprop, and then we optimize. All right, so now the gradient descent on the train set is we have given this large train set with n training samples. If you're looking at the dimensionality here, you should very quickly see that we have these issues with SGD, right? And we should figure out how we actually find the parameters for our mini batches, like how much we can fit. In practice, what that means is we're trying to make sure that we can have as large mini batches as possible, and then we can run SGD accordingly. Okay, so this is training, and training so far is only looking at the training set. But now, in the next few slides, I would like to close the arc back to the basic machine learning recipes. And this is what learning means now, right? So now, training means we're optimizing the parameters of our network to mimic or to best optimize, to minimize the loss function on our training set. And then we're hoping that this generalizes to an unknown data set. And so far, we haven't talked about this learning at all whatsoever, right? We've talked about it at the very beginning of these machine learning recipes, but we have not talked about it in the context of neural networks. And this arc I want to close here right now, right? So what we want to do is we want to train on a known data set with, let's say, images and ground truth labels. And then once we have that, we hope that based on this training set, the optimized parameters in our network will give similar results on different data that we have not optimized it for. For instance, the training data or the validation data. Now, how do we know that, right? Well, I mean, for the most part, if you're looking at data sets like ImageNet or so, right, you're going to have the split between training, validation, and test set. These images actually come from a reasonably similar distribution, right? They have been captured and recorded or like they have been collected more or less from the web with a similar method around. And so the distribution between the training, val, and test set, they're presumably very similar, right? But the whole hope here is, and hope is probably a good word for it, is that if our network is large enough and we're training it with enough samples, so we have enough constraints on our optimization, then we can actually generalize to unseen samples, right? Okay, so learning, how does it work? Well, we have these three things. We have our train set, we have our val set, and our test set. We do actually use the training set to train the neural network parameters, right? This is the only reason why we have the train set. We don't do anything else with it. The validation set is for hyperparameter optimization. And the biggest hyperparameter optimization basically is the learning rate. We check how generalization works between training and validation, right? And then testing, we mentioned this many, many times, but I want to reiterate it here in this context, is then done only at the very end, once we have finalized, like the hyperparameter optimization and so on. Never touch the test set during the development or training, right? This is it's basically cheating, right? If you're looking at the test set and then changing parameters, then you're basically using that information to cheat. Okay, so what are typical splits? So typical splits here are, in neural network land, we're gonna have training is about 60% of the data, validation 20%, and test maybe 20%. Or trains like 80, val 10, and test is another 10. During the training, we're gonna check our error that comes from the average of the mini-batch error. So we typically have this running average that we're tracking. We'll get to this in a second, how this looks like in practice. And typically what we do is we take a subset of validation every n iterations. And this is an important thing, actually. How do you validate, right? How do you validate is very tricky. So one way to do validation is you just keep the current network. You take the entirety of the validation set and you're going to run all your validation samples throughout your network, and you're going to get an error, an accuracy metric or whatever for your entire validation set. That's one way to do that. I'm always advocating do it differently. The reason why I want to do it differently is if you did it this way, like take the entire validation set, you typically do a validation like every epoch or something like this. And this is, I think, way too slow. I think practically you want to do a validation every iteration, actually. But since you don't want to run the entire validation set every iteration, what you do in practice, you're going ahead and say, well, I'm also going to just take a subset of my validation and I'm evaluating every few iterations. And then I have a running average of the loss for the validation, and I can track this simultaneously with the training loss, right? And this is almost no compute overhead because the validation error doesn't need a backprobe pass. So that's much faster to do. And you can probably do it like every, 5 iterations or so. So you're computing a running average of the error for both training and for validation. And then you can compare them during training already. And this is one thing that I'm gonna push for in the next few slides, in the next few lectures even. I'm going to argue the key to success in deep learning is make the training efficient. Get quick feedback, understand what might go wrong, and adapt very quickly. The people who are starting don't do that typically. When you're starting with this, you're running stuff for like a day, nothing, it doesn't work out the way you want, and then you have to restart the whole thing. The pros who have done this for a couple of times, they start a training process and after a few minutes they figure out, oh wow, this is not working, I have to fix something. So these quick iteration times means during training, we need to get some feedback, and that's how you get quick feedback. Okay, but now back to our basic machine learning recipe. We talked about this already, right? Like we talked about training, validation, and test, using the validation for our hyperparameters. And at the end of the day, we do testing. One thing we have not talked about is, in principle, it's pretty arbitrary which part of the training we are going to use, or like how we split the training and the validation, right? Because you have to find the right hyperparameters. And one very common way what people say is, well, actually it's pretty arbitrary. You take this part, these 20% for validation. Why don't you take the other 20%? And there's a concept called cross-validation. So what does that mean? Cross-validation means, if I go back, the obvious disadvantage is why don't we use these 20% also for the training? And this is not being used right now, right? So for cross-validation, the idea is we're actually doing a kind of a round robin here. So in the first run, what are you going to do? You're going to keep this part here as your validation, and this part here you're going to keep as your training. And in the next run, you just taking the next part as validation and take the rest as train. Right now you take this as validation and take this as train. And so on. And then you go all the way through. And then you continue, right? And this cross-validation is actually being widely used when you want to squeeze the last bit out of your training. Don't do this at the beginning, but do it at the end in order to find optimal hyperparameters, because in this case, the hyperparameters are influenced not just by the 20% of your training, of your data that you've annotated, but it's actually being influenced by a lot more, right? Because you took many different samples here from your data set, and because of that, you typically get better results. So this is a very common thing doing cross-validation actually in practice, especially when you don't have a lot of data. If you have infinite data, then not that important. But if you have very little data, and in practice we always have not enough data, then we want to do cross-validation. Okay. So cross-validation means we have training validation, we have our test at the end once we've done that, and then we can check how our stuff works. Now, what's our recipe right now? What do we have to do when things go wrong? How do we know when things go wrong? So a very common setting that we could have here is that if we are having a data set, right? Let's start at the very beginning. Let's say I'm taking 1 million images and I want to figure out, training my favorite classifier, how to detect cars in these images. So what I have to do is I have to take these 1 million images, I hire a bunch of people, they're going to put annotations on these images. So they're going to put labels on these images that telling them, is it a car or is it not a car? Presumably it's not just car or not, presumably there's more labels than this, but let's just keep it simple for now. In this data set, there will certainly be some errors, right? This is called the ground truth error. This does happen. Like, we don't want to talk about it, but the ground truth is not always the ground truth, right? Because everything is human annotated here in practice. So there might be some issues. So sometimes people don't recognize which one it is. ImageNet, for instance, is kind of notorious for that because, not saying ImageNet has a high ground truth error, but ImageNet has a lot of classes in it that the average human would not be able to tell apart. For instance, there's a lot of different dog breeds in there, and I have no clue which dog breed is which, right? So this is how you basically get ground truth errors in the dataset. That's the quality you're getting during annotation. Now what you do is you're taking the training set, you're training, and you're gonna get an error. And this error might be a 5% classification error here. So this is obviously going to be higher than the 1% we had before, right? It's not quite straightforward possible to outperform your ground truth data, right? Because the best thing in principle your network can learn is to actually follow the distribution of what's in your training set. It's not entirely true. There's certain ways how you can actually figure out how training in principle could be better than ground truth. But that's maybe a different discussion, but you can kind of see the thing. Like typically, if you're having a training curve, right, and you're optimizing that curve, you would very well see at some point that, well, at some point you cannot get any better. So your loss is not going to be zero suddenly, right? So you're not reaching the same exact predictions that the ground truth have because the data set is large and so on. But now, probably the more important thing is if you're now taking the trained model and you're evaluating the value of the test set, you typically get a higher error. Like 8% is higher than 5%. This is just the case example here, of course, right? And this case example means, well, we don't generalize as well as we hoped for. So in other words, we overfitted a little bit to our training set. And in practice, that's always going to happen, right? It's fundamentally very difficult to have a training error that is lower than the validation error. It's just not happening, right? This is just something then, if that did happen, then we would have a problem with our data distribution. In practice, if your training error is actually if your training error is higher than your validation, so validation performs better than training, probably something is wrong in your training. That's probably a safe bet. Okay, but what do we read out of these things? Why am I going through this in so much detail? Well, the point is the delta between these two is what's called underfitting, right? So how close can our training be to our ground truth? That's our bias. It's the underfitting part, right? So if this is too large, then we have to do something on the training side. If this one here, or the delta here between these two, that's the variance, that's the overfitting part, right? If the training can approximate the test, if the training error basically goes to 0, but we don't channelize, then we have not learned anything, unfortunately, right? We have done a great optimization, too great of an optimization maybe, and then we have a lot of overfitting. So now the basic recipe for machine learning is to balance these two pieces out. We don't want to be too large here, and we don't want to be too large here. So these two things balance out. And how do we do that? Well, there's a very simple mechanism now, which says, well, if my training error is too high, I'm taking, well, again, we're now in neural network land, right? Understand these things, they actually count for also non-deep learning machine learning methods. But the point in neural network land means if my training error is too high, that means my neural network cannot approximate the distribution in my training set very well. What do I have to do? I need a more powerful network. I need to figure out a bigger model. I need to train longer. I need to figure out my whole hyperparameters in the training. Is my optimization doing right? I need to figure out, is it the right model architecture? Do I need to use more layers? Do I need to change the distribution between depth and width of the network? Stuff like that. And later on, we're going to talk about things like convolutional neural networks, right? That may be a different type of architecture that we might need. So the training error too high means essentially our model is too weak. Our model has not enough capacity. It cannot very well approximate our training samples, and that's a big problem. If our, by the way, so if our train def error is too high, this basically is the validation error here, right? If that error is too high, we need more data, more regularization, or a new model architecture, right? So the problem basically, if my validation is too high, that means I'm overfitting too easily. So one common problem for that is my data distribution is too simple, or my model is too big. So what do I need to do? I need to go ahead and go through all these regularization things we've talked about. I need to pay maybe more annotators. I need to maybe capture more data. That's always a thing that might happen. That's the thing that is very easy for you guys to do because, you know, you have to spend a lot of resources at the beginning. But if you want to do, for instance, a company and you want to deliver a product, that's typically a thing that you have to do. Capture enough data to make things work. Yeah, and then, of course, right, There's other alternative things that can go wrong at the end of the day, but practice you have to balance these two things out, right? And again, I wanna stress this. We had this before, right? Like this overfitting and underfitting of the problem. Underfitting means my model is too weak. Overfitting means my model is too strong. Appropriate is the fine balance between these two things, and that's the whole concept of machine learning, right? And there's these fun considerations, right? If I can overfit to an infinitely large training set, then I'm golden because then I can channelize as well. Okay, we've also had this curve. This curve is kind of like if you're looking at the training error, the training curve right now, right? So if the training error goes down, we're doing great. And this is the validation error here. But I'm having a gap here that tells me how much I'm overfitting. So this is a very common scenario that your training validation curves look like these ones. And there's a sweet spot at some point in between here that tells you when your training error goes down and at some point the validation error goes up, then you're crossing the underfitting to the overfitting zone. And there's a way to probably go ahead and say, at this point, I might probably want to stop training, right? Because that's the optimal validation that I'm getting at this point. So if I'm getting the optimal validation, that would mean I'm golden and I have trained something very useful. Well, and the reason why we are looking at these curves is these networks are pretty difficult to debug, right? So the main thing, what we're going to do is, when we're debugging those, we're looking at these learning curves. And that's the thing we're going to talk about for quite a bit right now. And I'm giving everybody a hard time who doesn't have a training curve. If you're training a neural network and you don't have a training curve, then you don't know what's going on. That's the most important thing to set up before even training anything. You gotta know your training curves. And there's different tools for that as well. So a typical thing what you would do for training, you're setting up two things. You're setting up the loss and you're setting up the accuracy, or like the metric respectively. Accuracy in terms of a classifier, regression would have other metrics potentially. But you typically want to have both. And the reason why you want to have both here is you want to make sure that your loss function corresponds with your actual problem statement, right? So it depends on what loss function you've chosen. Like this may or may not correlate with your final goal, what you have, and that tells you how much your loss function is actually suited to the respective problem. But this is a very common graph here. It looks like this. I mean, this is copy pasted out from TensorBoard. TensorBoard is one of the tools that a lot of people are using these days. And I recommend everybody to set this up right away. Also to give you a, to avoid the confusion. So TensorBoard can be used, of course, with PyTorch and TensorFlow at the same time. So even if you're using PyTorch, and we're using PyTorch for the most part, TensorFlow can, of course, still be used. TensorBoard can be used, of course. Okay, and how does it look like? So these curves look something like this. Let's look at the loss curve here, right? On the x-axis, we have the number of iterations. On the y-axis, we have the loss. The absolute loss values that you have here are actually not that relevant. I mean, well, okay, you can look at it and try to interpret it, what they actually mean. What's more important is the relative trajectory of your loss curve. That's very important, I think. And then what we're seeing here is in the dark green line, this is the average loss. And you're seeing these light green, like jittery things here in between. That's basically the current loss of each of the samples. So the way you want to debug your loss curves is basically you're taking a running average out of your loss function. And out of this running average, you're going to figure out how your loss should behave and how it should look like. And in this case, your loss goes down, right? This is the high level trend, even though locally it's still chittering around a little bit. But this is the nature of SGD. SGD will look like the actual loss that SGD produces is the dark green one here, is the light green one, right? The light green one is jittering much more, and the dark green one is then the average, but we want to smooth it. And there's typically in TensorBoard, you have the smoothing parameter that tells you how much you should average your losses. Same counts for accuracy, right? You see it's very noisy here, but the dark green curve is basically what we care about. Okay, so is this a good loss curve or not? Well, what characterizes a loss curve? Well, a loss curve starts with a high loss, and ideally, once we're doing SGD and iterating, this loss goes down. So it means, well, we're converging, which is good, right? That's pretty good. The value goes from high to lower. That's also pretty good. Question is, could it go even lower, right? Maybe we need to change the learning rate schedule. We look at this curve, what we had before, say, well, yeah, maybe it could go lower. Maybe we should actually reduce the learning rate a little bit more. What we see here is, well, this loss at the beginning already converges relatively quickly, right? So maybe we should have reduced the learning rate here a bit more, but globally, this is how, a reasonable loss curve will actually look like. Now, I also mentioned it, we don't just want to look at the training loss. In practice, we want to look at the validation loss at the same time. So then the curves look something like this. Different tool, but just get the concept for now. So here we have two losses, the training and the validation loss. We have here the loss on the y-axis, and we have the epoch on the x-axis. And now what we see is both losses here go down, and the more they go down, the further they spread apart, right? So here basically the training loss goes down faster than the validation loss, which doesn't go as fast down. So there's a little bit of a generalization gap. But this is a curve I would say, well, it's not terrible, right? So it does go down. The thing what might not be ideal on this curve is it should go down a little bit more like this. The reason is basically this is an indication, like if I look at a function or a loss curve like this one, I would say, well, maybe probably your learning rate is a little bit too low. You probably want to have a bit of a higher learning rate. And maybe there's a little bit of overfitting going on, right? Maybe we need to figure out a bit more regularization and so on. So here's another example. Here the training starts, validation starts lower. Typically the validation starts lower because it starts a little later, right? Like depending on how you evaluate. They both go down and they stay there. And they go down very, very quickly. So this is something where I would say, well, you know, you have probably this might be a too large learning rate. So here the question would be, should you reduce the learning rate a little bit, right? And now you balance these two, right? Like you figure out, okay, how much do I need to change my learning rate and so on. But none of them have crazy overfitting. There's a little bit of overfitting here. There's no overfitting here whatsoever. So these are reasonable train well curves. And they help you right now to debug your model, right? The one thing I mentioned before was make sure whenever you're setting up a training that you can plot the training and the validation loss during training. So you see, right, we're getting here values all the time. Depending on how fast an epoch is, you might have to have multiple evaluations on a subset of the validation after every n iterations. Because you need to know whether your validation goes down. If your validation doesn't go down and you have kind of this, this gap between training and validation growing, then you know something is wrong. And the key is to know this very, very early on. So you want to have your log being visualized in real time kind of, so you know what's going on there. Okay, so these are reasonable curves for the most part, right? I mentioned a few things. Maybe here the learning rate is a bit too small. Here the learning rate might be a bit too high. That's probably what's going on here, right? These are typical curves where you see massive overfitting. So here this is a bit more crazy, meaning that the training goes down pretty much straight, but even at the very beginning you see the validation doesn't go down anymore. And this is what I meant by looking at the curves early. So if I'm looking at this graph here, I see that this function here goes down a little bit, but then plateaus already here after like these, whatever, 20 epochs or 20 iterations, whatever this means. Then you see, okay, validation doesn't go down anymore. So we have an obvious issue here, right? And that's a thing where we have to intervene very early on. So when the loss here in the validation doesn't go down anymore, training goes down much further. I don't have to train until here. I know immediately already here, I have to change something, right? And that is quite critical to do this early. And you see it in the curves. Or you might get curves that look like these ones. So here you see already there's like massive spikes here going on. This is not good, by the way, if you have these massive spikes. You shouldn't get those ones. But you also see there's also pretty intense overfitting going on very quickly. So there's something wrong with these spikes. This is, I would always check what's happening there. Which training sample or which validation sample causes that. Yeah, check out this kind of stuff. And then here you have a massive overfitting problem at the end of the well. We have a few more curves here. Yeah, this is also a classic underfitting one here, right? Loss is still decreasing, but you see here already, right? I mean, we need probably a larger model, right? It doesn't go down as fast at the beginning. We need to train longer. It should go like this, right? These are good curves. This was a very canonical curve. Maybe it could go down more, but this is a canonical curve. Whereas this one here, this is not a good curve. It takes too long. It goes too slowly at the beginning. There's not a lot of overfitting, which is great, but this is a classic, classic issue here. And this is another thing that I mentioned a couple of times. If you get a curve like these ones, where your validation set is, well, your validation loss is lower than your training loss. This is something, again, that should never, ever happen. If that happens, validation set is easier than your training set, or you have a bug. For the most part, you have a bug, because if you take a public data set, like for the most part, the validation and the training set, they kind of are from a similar distribution. They're equally difficult. And that means you have some issue in your code. So if that happens, you already immediately know that something is wrong, right? So yeah, you can basically interpret a lot of stuff here from these curves. And I think that is fairly critical to actually, make practical progress when training your neural networks. All right. So if we're summarizing this here, so what did we talk about? We talked about underfitting, where training and validation losses decrease even at the end of the training, but we didn't train that much. But underfitting could also mean that they actually converge, but the model is not large enough. So if your model is too small, then your loss doesn't go down enough, but they still do converge and they don't go down anymore, right? Underfitting could mean both. Overfitting means, well, we have a gap between the validation and the training. It doesn't necessarily mean that the validation loss has to increase. It just means that there's a massive gap between the two loss functions, right? So for instance, here the validation doesn't increase, but the training just goes down a lot more, right? So overfitting means always, well, training is much better than validation, and that's an issue. Now, the ideal training is, we want to have a small gap between training and validation. Both have to go down at the same rate. They should be stable. There should be no noise. The validation should not be higher than the validation should not be lower than the training loss. That would be also an issue. But yeah, there's a small gap between the training and the validation. That would be the ideal thing, what we want to achieve for the most part. But it's of course not everything. We want to have, there's a small gap, and we want to make sure they're both low, right? So it doesn't help us if the gap is small, but the training loss is too high. Then we're in an underfitting case, right? So we want to have low training and low validation, and this is the way how we debug it. Okay, couple of more things. Bad signs. This is very, very important to notice at the beginning of your training. So you don't want to have to wait until the end of your training. You want to notice right away at the beginning what's going on. So if your training error doesn't go down, something is wrong, right? Training loss should go down. That's the whole purpose of training. If that one doesn't go down, something is wrong with the optimization. If validation doesn't go down, that's also a problem. Then we don't generalize. Then we're not learning anything, right? Again, when somebody tells you the term learning, it means validation has to go down. We have to figure that out. All right. Performance better on validation than on training. We've talked about this one. Test on train set different than during training. That's also important, right? And there's this usual bad practice. Training set contains test data. Debugging algorithm takes test data. Don't touch the training. Don't touch during training anything from the test set. That's very important. Okay. Hyperparameters. We've talked about that one a lot. There's the architecture choices. There's the number of layers, number of weights, how to distribute them in the network, what operators you're using, what activation functions you're using. The optimization itself is a hyperparameter, right? Like how many iterations do we run it? How many epochs? Learning rate is, learning rate, most important one. Solver parameters, decay rate, and so on. Regularization is important. We'll talk about this one soon. There's a lot of ways how you can regularize. Things like batch size is important. This is a good thing we haven't talked too much about. The batch size, you can see this typically in these curves. If the curves of the raw updates, right? So if we're going quickly back here, if this stuff here is fluctuating a lot, that means your batch size is too small. So larger batches should be more stable, right? So that's important. Batch size you want to have as large as you can, depending on how much GPU memory you have. There's a way, I'm not sure if we have it on some of the slides, but one thing I should mention here. For the batch size, you can trade compute for memory, kind of. There's a thing called gradient accumulation. It's pretty straightforward. So all you do is you just have a couple of iterations, accumulate the gradients, and only then do an update step. So you're trading compute for memory in a sense. So it's slower, but you get more stable gradients. So sometimes you might want to do that if your problem is a little bit unstable. Yeah, so overall, learning setup plus optimization, that's what our hyperparameters are. How do we tune hyperparameters? Well, there's the manual methods. That's what we have done for the most part, or what we've talked about for the most part. You're looking at your curves, you check out what's going on, you're changing stuff, you look at your curves again, and so on, and then you iterate. There's more practical ways how to do that as well. There's a thing called grid search. Grid search means you have a structured way how to go through your parameters. You need a lot of GPUs for that one, right? So grid search means it's structured. You just like have a bunch of for loops. You go through a bunch of hyperparameters. You check it out, which one works best, depending on your ranges of all the parameter spaces, and then you select the points accordingly. Typically, people use some sort of pseudo uniform distribution here until they iterate over all possible configurations. There's also complete random search, right? Like in grid search, but just pick points at random in predefined ranges. So, right, this is the difference kind of from a visualization standpoint. It really depends on the problem, what you're dealing with. For the most part, you also don't do naive grid search over all hyperparameters. For most part, you do a grid search at some point over the learning rate. That's the one thing people do. But yeah, like hyperparameter tuning automatically is going to be very expensive computationally speaking, right? Because basically everything is a run. Now, one thing we've already learned, how can we make this faster? Well, we might not have to train always at the end. We check our training curves, on validation curves, and then we see, how this might go a little bit faster. All right, so this is how we do it. Now, the next slide, this slide here is probably the most important concept for everybody. And it's a bit counterintuitive, but it's very important how you get started. So when you want to get started, you want to start as simple as you can, right? And what does that mean? You want to debug things one by one. You check, oh, this works, then that works, and so on. And this is how we do that. So the one thing, how we're going to start is we are starting with a single training sample and we're overfitting to that sample, right? I'm not expecting anything reasonable to happen here. I don't even have a validation here at this point. All I'm trying to do here is right now, I'm trying to make sure that my model, which presumably has like a lot of parameters, this model can overfit to a single training sample, right? And I want to check if this output is correct. I want to make sure that the model can pretty much overfit, get 100% accuracy, and can just memorize that input, right? To be precise, in this case, it doesn't even matter what the input is. It just memorizes the output actually, right? Because it doesn't matter, it's always making the same prediction. In this case, when you have a single training sample, you're checking, can your model or can your code load your data from the target predictions, from the labels? And can you have an optimizer that memorizes this target data? It doesn't care about the input in this case, right? Because it doesn't matter. It's always the same output. And in this case, when you're starting like this, you're turning everything that is complicated off. Like, we're going to learn a lot of complicated stuff or like advanced stuff in the next few lectures. You turn everything off. There's like no like craziness in terms of what layers. It's a simple model, very straightforward, like no regularization and so on. You just want to overfit for now. Once this one reaches basically a loss of 0, and you have to, and this is very easy to explain. This should take seconds to do, maybe minutes, depending on how complicated it is. But typically this is very, very fast. You can do this live, check the loss curves, and see if it goes down to 0. And it should go down to 0, right? Then what you do is, once you have that one, then you increase to a handful of examples, right? So you increase to, let's say, 4 samples. Like 4 samples is still completely overfitting. There's no chance on earth that we would ever learn anything from that. But we don't care about it. It's just for debugging your code. So you increase to a handful of samples. And from these handful of samples, why do we go from 1 to 4? Well, the difference now is, now our model has to memorize 4 different outputs. But these 4 different outputs, they're now conditioned on different inputs. In other words, I need to figure out how to load the input correctly as well now. So the input-output pairs have to match, right? And this is important because now my data loader has to do everything right. It has to figure out the input and the output to work. And for that one, you still don't learn anything. You should still get pretty much a loss of 0. You should still get a training accuracy of 100%. And it should still only take, at best, a few minutes, right? And here, still 0 learning. This is just checking. Can I load data? Can I overfit? And here now, can you distinguish between different inputs? In other words, like, does my input loader work correctly, right? Okay, once you got that one, and this is always the first thing you do, at this point, you already must have set up training curves visualizations, right? You should check how this stuff looks like, and you should get a bit of a feeling of how your code and your data looks like. And only then, once these two things check out, you're gonna move from overfitting to more samples. And the way you do that is you move from like 5 to 10 to 100 to 1,000, right? And at some point you should see generalization. What does generalization mean here? Well, if you go still to a very small if you go still to a very small training set, you're still going to overfit. But at some point, and this is a big moment in your training process, at some point your validation should go a little bit down. As soon as your validation goes a little bit down, we know, we're learning something. And that's great. Because then, at this point, then you can throw more samples and more stuff at it, right? Okay, so I think this slide here is really important. I might reiterate it a couple of times in different versions, but this is really critical how you get started, right? You start very simple, and then you make it more complicated. Okay, finding good learning rate. We talked about this one. Use all training data with a small weight decay. Perform initial loss sanity checks like log C for softmax with C classes. Find learning rate that makes the loss drop significantly within the first 100 iterations. And then try a bunch of learning rate like these ones. All right, sorry, I had a couple of issues with the microphone, hit restart. So we stopped at the course grid search. So the whole idea is we're starting with a course grid search to get the high level results first, and then we're gonna fine tune and tweak. Refining means we pick the best models we found in the course grid, we refine the grid search around these top models, and then we train them longer respectively. First we try without learning rate decay, then we add the learning rate decay, and then we study the loss curves, most important tool ever. Okay, there's one separate thing that will become important very, very quickly. And that's the timings. And the reason why this will become important is if things are not very optimized very well, things take a really long time. And by long time, I mean it's impractical at some point, right? So what I also recommend is when you're doing these overfittings at the beginning, check out how long does each step take. Get precise timings, know how to take the timings as well, and check them out. If an iteration takes more than half a second, then it's a problem, right? It shouldn't take so long. It should take 100 milliseconds, 50 milliseconds for an iteration at most, right? And then you look for bottlenecks and get these timings correctly, right? So there's typically the things you have to check out is you have data loading, you're gonna have backprop, and you have to balance between these things. So if you're dealing with data loading, let's talk about data loading. So what could go wrong in data loading? Well, the resolution might be too large. My samples might just be too big. You could check out what your hardware can actually do. Are you training from an SSD or training from a standard hard drive? That might make a massive difference, right? Depending on how large your samples are. You could use compression. Like if you're taking images, are you loading JPEGs or are you loading PNGs? Right? Might be a massive difference. So basically, is it faster to decompress a JPEG or is it faster to load a PNG raw? But you don't have to do as much compute. Common things are, I know everybody uses Python. In Python, doing stuff on the CPU could be really slow, right? You have to be clear when you're running a for loop in Python, that might be a that might be another level. And you might have to time these kind of things. The one thing, we don't have too much time right now in this course, unfortunately, to go over it. But one thing is really critical to understand is how timings work when you're running stuff on the GPU, right? The way you're running stuff, the computer has a CPU and a GPU, right? If you're executing some code on the GPU, the way this works is you have in your code, in your CPU code, you say, do some stuff, run a kernel or run some backprop or whatever on the GPU. If you measure the time it takes to execute that code, it's like 0 because it doesn't do anything. The GPU execution is asynchronously, meaning as long as I don't read back any results from the GPU, like this will just run in the background and my CPU code will respond. It will not wait until this operation finishes. And that's the problem when you do timings. So all of this stuff uses CUDA under the hood. And the problem there is basically you have to make sure you do a device sync. In CUDA, this is called CUDA device sync. But you have also like event timers in CUDA, for instance, how you time this properly. And this is critical when you do timing of neural network stuff that runs on the GPU. Be aware that GPU calls are asynchronous. Maybe later we have a bit of more time, but I have to check. But this is really important actually to understand the timings in the GPU. You have to be aware that they are executed asynchronously. Yeah, and then like globally speaking, apply a bit of common sense. Like there's not a lot of like high-level math right now behind it. Now it's just a bit of common sense, right? Like estimate the total amount of time, how long it would take. You see some pattern in your training curves. How long will it take to converge roughly? Is it still going down? How long did you train so far? Does longer training still make sense? And so on. So this is very, very important. And if you just have a bit of common sense, I think you will very quickly realize, how to add these things together. The other part, what I think is super important, is the network architecture. A frequent mistake, and this is the most common mistake, I'm seeing this unfortunately all the time. People start with, they read a paper or they read something online, they see, wow, this is like such a cool result, I want to replicate that. And then they're going to use this really large network, they're going to train on it, and then they see where they stand. And then what happens is, after 2 weeks of training, they check they had an error in the data loader, right? And then they have to train another 2 weeks. And this is obviously not feasible to start with any state-of-the-art network at the beginning. That's what I was trying to say before. Start very simple. Start with a small network, the smallest network you could even imagine. Yeah, rule of thumb, divide number of layers by 5 or by 10 even, right? Start with a very small network. I mean, I'm saying a small network is not millions of parameters. Small network is smaller than that. I mean, it depends obviously on the problem, but the point at the beginning is not to achieve state-of-the-art results. The point at the beginning is to figure out, do I load my data correctly? Does backprop work? And then eventually, do I do any learning at all? If my validation doesn't go down on a smaller network, it's not going to go down on a larger network, right? That's just how it goes. And the point is, you want to get your debug cycles down. That's the number one key to setting up stuff. And I know this is an advice that is very difficult to take because there's a lot of open source code online and it's very tempting to just take some stuff, download it. But there's always the producers and there's the consumers. Of course you can run an existing code that other people have done. But the problem is if you have to write your own code and if you want to be a producer, then you have to know how to do this debugging and so on properly. Right? And this brings me to the debugging, which means, check out your training validation curves. Evaluation needs to be consistent. Numbers need to be comparable. Make only one change at a time. This is another thing I see all the time. I've added 5 more layers and double the training size. And now I also train 5 days longer. Now it's better, but why? Right? So always do one thing at a time. Train. You don't have to train till convergence necessarily, right? That's why you have the curves. You see stuff early. So that's why this is really critical. And then you go ahead and visualize the input, prediction, ground truth, and so on. So common mistakes there in practice are, did not overfit to single batch first, forgot to toggle train eval mode for networks. We'll later check about this one when we talk about dropout. For getting to zero the gradients, that's also common when you have the old gradients in there and they're just accumulating. Pass softmax output to a loss function that expects lower logits, also very common. These are just common things. We're probably going to talk in the practical sessions about this one a little bit more. But yeah, check out this stuff, apply common sense, and start simple. That's the main thing. And yeah, and then the final thing I wanted to just iterate quickly was we talked about TensorBoard. TensorBoard, in my opinion, is the #1 visualization tool, and you got to set it up, right? I mean, of course, we're going to use PyTorch. It's unlikely we're going to use TensorFlow, at least not for this course. There's going to be a lot of visualizations in practice that we have to get right. We have our training and our validation curves. We've talked about this one a little bit. This is how it looks like, right? Here you have the smoothing factor, what I mentioned, so you can smooth it. You can compare the training and the validation curves and the accuracies respectively directly in one chart. You can select many curves, how to compare. You can compare different runs at the same time, right? So here you can select which runs are being used. And then you hover over it and you see exactly what the loss values and so on are. You can even go ahead in TensorBoard and visualize the model predictions, right? Also very common. So you have like images, especially when we're talking about generative models later. That's very, very common. You can do this like also every n iterations basically, right? Of course, check the compute, where the bottleneck is, does it even make sense to do it? But you have to get debugging stuff going. Otherwise, you don't know what your network's doing. You can visualize confusion matrices very handily here. I think that's pretty cool. You can compare hyperparameters. Yeah, I mean, this is just something you have to try out. I think this is really, really critical. How hyperparameter runs and so on give you different results, and you keep track of your experiments. The #1 thing that distinguishes the amazing deep learning people is they actually have very good bookkeeping. They know how to track their experiments. They know early on, based on their loss curves, how long they need to train stuff and whether the experiment has any chance of success. And then they adapt very quickly, right? And this is the thing that really distinguishes the more experienced people there. All right, with that one, we are pretty much at the end. It's a bit shorter today. In the next lecture, we're going to continue about training neural networks, about output function, loss function, activation functions. Check the exercises. Otherwise, thanks a lot for joining. I hope you enjoyed it. I think we're getting more and more exciting tools available now every week. So I hope you're still keen on training your own networks and you still enjoy it. I am certainly very stoked right now. And I hope to see everybody again for the next week. Thanks a lot. See you and bye-bye.